Welcome to the course on coding theory. In this lecture, we are going to describe how we can use error correcting codes for error detection and error correction. So, we will first describe what we mean by syndrome, and then we will show how we can use the syndrome to do error correction and error detection. So, this lecture is about syndrome and error correction and error detection. We will first talk about what is a syndrome and how we can use it for error detection, and then we will talk about how the syndrome can be used for error correction. So, we know so far if we have an nk linear block codes, so that means we have k information bits and n coded bits, and this nk linear block codes is completely described by a generator matrix and a parity check matrix. So, let us assume that we have a code word which is encoded using a linear nk block encoder. So, we have an output of a encoder which is of coded bits of length n. Now, we want to transmit this code word over a communication channel. For simplicity, let us consider a binary symmetric channel. Again, let us recall what is a binary symmetric channel. So, in a binary symmetric channel, we have two inputs and two outputs. So, binary inputs 0s and 1, binary output 0s and 1, and with probability let us say probability 1 minus p, we receive the bits correctly, and there is a crossover probability of p that the bits get flipped. So, this is a binary symmetric channel. Let us denote by R our receive sequence, receive code word which we sent over this binary symmetric channel. So, the types of, as I said, the output of the binary symmetric channel is also 0 and 1. So, we can describe the output of a binary symmetric channel R as our transmitted code word plus some error vector. So, our transmitted code word is an n bit tuple. Similarly, our error vector is also an n bit. So, we describe our error vector by E0, E1, E2, En minus 1, and whenever an Ei term is 1, that means that particular bit was not received correctly. So, we can write an output of a binary symmetric channel. So, the first bit that we would receive is basically V0 plus E0, V1 plus second bit will be V1 plus E1, similarly V2 plus E2, and last finally we will get Vn minus 1 and En minus 1, where this E0, E1, E2, En minus 1 is my error pattern. Now, when does an error occur? If my receive sequence is not same as my transmitted code word, then this is an error. So, the error is 1 only if my receive bit is not same as my transmitted bit. If the receive bit is same as my transmitted bit, there is no error. So, that I will keep that bit Ei as 0. Okay. Now, if a particular bit Ei is 1, what does it denote? It denotes that ith bit is in error. Now, when we are sending this code word over a communication channel, what are we interested in? We are interested to find out whether any error has occurred. If any error has occurred, we are interested to find out the location where the error has occurred, so that we can correct those errors. Okay. So, first we are going to show how we can detect error. So, we define a term which we call as syndrome. What is a syndrome? Syndrome is computed by computing this R H transpose. So, R is basically 1 cross n vector, H is my n minus k cross n vector. So, H transpose is n into n minus k matrix. So, this term R H transpose is known as syndrome, and this is when this is non-zero, that indicates there is an error. So, R is the code word if and only if the syndrome is 0. So, whenever the syndrome is 0, basically if the syndrome is 0, then R is a code word if and only if syndrome is 0, and this is easy to check, because we know that if V is a valid code word, then V H transpose will be 0. So, if there is no error, my received sequence R would be just equal to V, and then the syndrome would be V H transpose, which is 0. And if syndrome is not equal to 0, then it means there is an error. Now, if the syndrome is 0, does it always mean that there is no error? No. There is a category of error which we call as undetected error. Now, when does an undetected error happen? If your S is 0 and your received sequence R is not the code word that you transmitted, but some other code word. Let us say I transmitted a code word V1 and my error E was such that it transformed it into another code word V2. So, received sequence is V2. Now, if I compute syndrome, because V2 is a valid code word, then VH transpose will be 0. So, an undetected error happens when your error pattern is such that it transforms your one code word to some other code word, and that is what we have written here. So, if S is 0 and R is a code word, that means no errors are detected. However, if R is a code word other than the actual code word transmitted, then an undetected error has happened, and this happens when an error pattern is a non-zero code word, because we have said a property of linear block code that sum of two code words is also a code word. So, for this scenario to happen, this E has to be a valid non-zero code word. So, as I said, we compute the syndrome from the received sequence R. The interesting part is syndrome depends only on the error pattern, it does not depend on what code word was transmitted, and this is easy to see. So, syndrome is RH transpose, which we can write R is my transmitted code word plus error vector, this whole multiplied by H transpose. So, this I can write as VH transpose and EH transpose. Now, what is VH transpose? VH transpose is 0, because V is a valid code word, then syndrome is nothing but EH transpose. So, syndrome does not depend on transmitted code word, it only depends on the error pattern. So, I have an example here of a 7-fold linear block code whose parity check matrix is given by this. Now, let us say my received coded sequence is this, and I am interested to find whether there is any error in this received sequence. So, how do I do that? So, first I will compute the syndrome. So, what is syndrome of R? This, so syndrome is R H transpose. So, R is this and H is given. So, H transpose is basically 1 0 0, 0 1 0, 0 0 1. So, this is my H transpose, and when I multiply this, so I multiply this by this, multiply this by this, multiply this by this, what I get is 1 1 1, which is not 0. That means there is an error in my received sequence. As I said, the syndrome only depends on the error pattern, it does not depend on transmitted code word. And if you have your parity check matrix in a systematic form, then you can write your syndrome equations in terms of your error patterns like this. So, these are your basically n minus k syndrome equations. So, to recap what we have said so far, we have said that for error detection we need to compute the syndrome, and if the syndrome is non-zero, that means an error has occurred. Now, we will move into error correction, and we will talk about how we can use the syndrome for error correction. So, as we saw basically from the syndrome equations, we had basically this was 1 cross n and H transpose was n cross n minus k. So, we essentially had n minus k syndrome equations. So, we had total n minus k equations, and how many unknowns we have? We have n unknowns from location error at location 1 to error at location n. So, we have n unknown E0, E1, E2, En minus 1, whereas we have only n minus k equations. So, we have less equations, more unknown, and what we need to do is we need to solve this set of equations to find out what these unknown quantities are, because to find out the error pattern we need to know what these EIs are. Okay. So, we need to solve these set of n minus k equations to get back our corrected sequence, and our what would be a corrected sequence? So, our estimated code word would be nothing but R receive sequence plus estimated error pattern. So, we need to, when we do error correction, essentially what we are trying to do is we are trying to estimate what the error pattern is. So, as we can see from here, because we have n minus k equations and n unknowns, we have total 2 to the power k solutions of these n minus k equations. So, there are total 2k solutions to this syndrome equation, and out of them there is only one which is the correct error pattern. Out of those 2k solutions there is only one error pattern which is correct. Now, how do we choose the most likely error pattern from these 2k solutions? How do we choose the most likely pattern? That is basically what our objective is. So, when we try to minimize probability of error, we want to choose the most probable error pattern. We want to choose the most probable error pattern from those 2k solutions of this set of equations. And as we said, we did an exercise in previous lectures. We have shown the decoding rule for maximum likelihood decoding rule for a binary symmetric channel, and we have shown that for maximum likelihood decoder we will choose our estimated code word as one that will minimize the Hamming distance between the received code word and the transmitted code word. In other words, which would minimize the Hamming weight of the error pattern E. So, from the 2k different solutions, basically the one which has the least Hamming weight, that is the best solution for a maximum likelihood decoding rule for a binary symmetric channel. So, let us take an example now. So, we have a 7-4 code whose parity check matrix is given by this, and our transmitted code word is this and received code word is this. We can see that there is an error in this location. This was transmitted as 1 and this was received as 0. So, there is an error in this location. Now, how do we find out that there is an error and there is an error in this location? So, first thing that we will do is we will compute the syndrome. When we compute the syndrome, which is RH transpose, what we get is a non-zero. And since this is non-zero, this means there is an error. Now, next step is to find out where the error has occurred. So, in this case, we can write the syndrome in terms of error bits. So, we have 3 equations and we have total 7 unknowns, right, and these equations are basically given by this. We have our H matrix given by this. This is our error pattern. So, when we compute EH transpose, we get these set of 3 equations, and there are 16 solutions to this set of equations. This set of 3 equations where there are 7 unknowns, there are total 2 to the power 4 different solutions, and these are the 16 different solutions. And as we said, the maximum likelihood decoding rule for a binary symmetric channel will choose an error pattern that has minimum Hamming weight, so which has minimum number of ones. So, you can see among these 16 solutions, the one that has minimum Hamming weight, minimum number of ones is this. All others have, this has 4 ones, this has 4 ones, this has 5 ones, 3 ones, 2 ones. You can check, basically this one has the least number of ones. So, this error pattern has the least of Hamming weight. So, this is out of those 2 to the power 4 solutions, this is the most likely solution, and this we can verify also, because we were given the receive sequence and we knew the what were the transmit sequence was. The error pattern indeed was this, which we found out from by solving this set of equations. So, to recap then, now when we want to do error correction, what do we need to do? We need to solve for this syndrome equations, and there are n minus k equations, but there will be n unknowns. So, this will have 2k solutions, and we will have to pick the most probable solutions from these set of 2k solutions. The next lecture we are going to talk about a general decoding algorithm for a linear block code. Thank you.